In this video, I'll talk about how we answer questions 2, 20, and 21 on Achieve Section 3.8. Number 2 actually starts off with a good precursor of everything that you're going to be doing in the next class in integration. It gives you a specific derivative and it asks you which of the 6 inverse trig functions would be the original function such that this is g prime of x. So the one I had here on my Achieve account was -1 over the square root of 1 minus x squared. Well, I'm supposed to remember that the inverse sine has the derivative of 1 over the square root of 1 minus x squared. The inverse cosine is -1 over the square root of 1 minus x squared. So it's saying what original function would give you this? I can say, well, it's the inverse cosine of x. I could also call it the negative of the inverse sine of x, and that should also be correct, but this is the more straightforward answer there. So if they give you something like 1 over 1 plus x squared, you know that your original function would have been inverse tangent. So you just have to work backwards to see what original function is going to give you the derivative given in the problem. Okay? Up next, number 20. This one jumps up its difficulty level quite a bit. There's some algebraic simplification that we need to do in this problem. So the inverse cosecant function has the derivative of -1 over the absolute value of what's inside of it on the square root of what's inside of it squared minus 1. Now notice how I used that within the formula. I was originally thinking of this as a product rule where I have 6 times the inverse cosecant. We know the derivative of 6 is just 0. So then you say plus the first 6 times the derivative of the second. Well, derivative of the inverse cosecant is -1 over what's inside of it, inside of an absolute value, on the square root of what's inside of it squared minus 1. And then I multiply by the derivative of what's inside of it. Well, the derivative of x to the -8 is going to be -8x to the -9th power. Now I can say, okay, there's a lot of simplification. I don't want any of those negative exponents left in there. So first of all, what I did is I just said, well, I could go ahead and multiply my constant coefficient. 6 times -1 times -8. That just gives me 6 times 8 is 48. And I know that this x to the -9, it's a factor of x to the 9 in the denominator. And the only other thing I did in this step was I just said, well, if I have -8 to the second power, that's -8 times 2. That's the -16th power there. Now, from this step to the next, what I did is I simplified and I said, well, now if I'm multiplying by x to the -8 and an x to the 9th down there in that denominator, well, anytime you multiply like bases, you add their exponents, and I can say, well, that's going to be x to the first. I went ahead and left it inside of an absolute value. You wouldn't need to, but certainly not wrong to. So I went ahead and put it inside of an absolute value there. Now the problem was, after I collected those, I was looking at it, and I still have a negative exponent on the inside, on the power on that x inside the root. So I need to get rid of that -16th power inside the root, so I need to multiply by x to the +16 inside of a root. Now, of course, you understand that the square root of x to the 16th, I'm really multiplying by an understood x to the 8th over x to the 8th. When I multiply by that x to the 8th in the numerator, that's where that comes from, 48x to the 8th. I left my absolute value of x, and then I distributed that root of x to the 16th into each of the terms inside the root. And when I did that, the first term, x to the -16th times x to the 16th is 1. And of course, 1 times x to the 16th is where the minus x to the 16th comes from. So now I've multiplied by this understood 1. I have a much better answer. One further step, now that I have a factor of x in the numerator and denominator, I can and should reduce that down. X to the 8th over x is x to the 7th. No need to put an absolute value, so I'll just say 48x to the 7th over the root of 1 minus x to the 16th. That would be a gorgeous final answer to that question. The next one here, it's a bit tricky. Not too bad though. So it's asking us to look at inverse trigonometric functions within a quotient rule. Of course, we also know that our inverse cosine and inverse sine have a very similar derivative, inverse cosine being -1 over the square root of 1 minus whatever's on the inside of it squared, inverse cosine being +1 over the square root of 1 minus whatever's on the inside of it squared. So the first step here, this is a quotient. I used the quotient rule. I squared the denominator. I brought that denominator to the numerator times the derivative of the numerator. Well, derivative inverse cosine, -1 over the square root of 1 minus whatever's on the inside of it squared. So I was thinking, well, that's 10x quantity squared. That's where that 100x squared came from there. And all of that's under the square root. But then where did this 10 come from? Remember chain rule. You say, well, this is the derivative of the inverse cosine of 10x times the derivative of what was inside of that function. Well, times the derivative of 10x is times 10. So now I have my denominator times the derivative of the numerator minus the numerator right there. Now times the derivative of the denominator. And it's extremely similar. You just say, well, inverse sine of 10x and inverse cosine of 10x, they have the exact same derivative, except for the inverse sine is positive. I still have to think of the chain rule and times 10. Now, this would be a horribly sloppy answer if you tried to leave it like this. So in order to clean up this answer, what I said to myself is I would like to get rid of those fractions in the numerator. Both the first and second term are being divided by 1 minus the square root of 1 minus 100x to the second. So you'll see I multiplied by an understood 1 by multiplying by that square root of 1 minus 100x to the second in the numerator and the denominator. When I multiplied by it in the denominator, I just brought it out in front. When I multiplied by it in the numerator, it's going to cancel that term out, and notice your first term is just going to be -10 times the inverse sine of 10x. That's where that comes from. Your second term, again, minus, and you would have 10 inverse cosine of 10x. Simplified answer right there. That would be a good final answer. You could simplify the trigonometric functions further by recognizing that inverse sine of 10x plus the inverse cosine of 10x is equal to pi over 2, but that's not necessary here. This would be a good final answer as it is.